Hi, everybody. Welcome to this session on trajectory prediction and trajectory and queue management. We'll have 4 papers this afternoon from all over the world. We have a first talk from Japan, and we have talks from the US and the European side as well. So I'm going to introduce myself. I'm Nicolas Durand. I'm a professor at ENAC in Toulouse. Behind me, you have a map of Spain. It's about the north of Spain here, right here, just here. That's where I'm staying right now. So our first talk, we're going to begin with our first talk for 40 minutes with a presentation first, and feel free to put questions and in the Q&R or in the chat, and I will read the questions after the presentation. Our first talk is from Daichi Toratani. Daichi, you can start sharing maybe your screen while I introduce you. So Daichi Toratani is a senior researcher of Electronic Navigation Research Institute, the ENRI Institute in Japan. His research interests include air traffic management and unmanned aircraft systems, in particular, applications of optimization, simulation, and system design. I'll let you introduce your talk, and we'll speak again after your talk with questions. It's up to you.
Yes, thank you, Nicola. Can you hear me?
Yes, we hear you very well. We can see your presentation.
Yeah. Hello, everyone. Good morning, good afternoon, and good evening. Thank you for joining our session. I'm Daichi Toratani from Electronic Navigation Research Institute, ENRI. I have 2 co-authors, Yoichi Nakamura and Megumi Oka. They are my colleagues. The title of our presentation is Data-Driven Analysis Method for Calculated Time Over in Air Traffic Flow Management. And this is a table of contents of our presentation. So let me move to the introduction. Due to the limited capacity of air traffic control, such as the processing capacity of the air traffic controller and the runway capacity at the airport, the traffic demand should not exceed the capacity of the airspace and airport. To prevent excess demand, air traffic flow management, ATFM, is widely used. When congestion in an airspace or airport is predicted, ATFM regulates the air traffic flow using various techniques, such as ground delay, minutes in trial, miles in trial, speed reduction, and rerouting. These techniques are called Traffic Management Initiatives, TMIs. In addition to these TMIs, the Japan Civil Aviation Bureau employs the Calculated Fixed Departure Time, CFDT, also known as the calculated time over, CTO, which is a promising technique toward 4-dimensional trajectory operations. The CFDT is one of the TMI that assigns a time to fly over a specific waypoint for in-flight aircraft. This figure shows the overview of the CFDT operation. When the ATFM system predicts excess demand for an airspace or airport, the system shows a CFDT assignment to an air traffic controller. The air traffic controller instructs the pilot to cross the CFDT at the assigned CFDT. The original ETA at the CFDT fix is 9:27 in this case, while the CFDT is assigned as 9:30. So the aircraft must delay the time over by 2 minutes. The pilot judges whether the aircraft can comply with the assigned CFDT and replies by either accepting or rejecting the CFDT. The method for delay is determined by the pilot. However, in most cases, the cruise speed is changed. An operational trial of the CFDT began in 2011, but was interrupted in 2014 due to technical reasons. With improvements in the operational procedure and ground systems, a trial called Shadow Operation beginning in 2020 is currently underway. In the shadow operation, the CFDT is not instructed to the pilot, and the aircraft doesn't actually change the cruise speed. Instead, fundamental data regarding the CFDT operation are collected. Through analysis of the data collected in the shadow operation, the CFDT will resume in actual operation. A critical problem in the previous trial operation was the high rejection rate of the CFDT by the pilot. A high CFDT rejection rate disturbs air traffic and increases the workload for air traffic controllers and pilots. One obstacle to achieving the high acceptance rate is that the ATM system cannot calculate whether the aircraft can comply with the assigned CFDT. Since the ATM system is a ground system, it cannot derive several important parameters for the CFDT, such as achievable airborne delay. Achievable airborne delay of the CFDT target aircraft. If the ATM system can obtain exact achievable delay of an aircraft, it can prevent CFDT rejection by assigning the CFDT within the achievable delay. The achievable delay highly depends on the acceptable minimum cruise speed. In actual operation, the acceptable minimum speed is not determined only by the aircraft specification, such as stall speed, but determined by the pilot considering various flight conditions. The acceptable minimum speed differs for each flight, so the ATM system cannot calculate the achievable delay on the ground. The goal of this study is to design the CFDT operation with a high acceptance rate. To achieve this goal, we developed the estimation method for the achievable delay and acceptance rate by using the CFDT operational model and collected data in the trial operations. By analyzing the estimated acceptance rate, this study can contribute to establish the best means of implementing CFDT operation. Next, I will explain the CFDT operational model. To estimate the achievable delay and acceptance rate of the CFDT operation, we developed the CFDT operational model. Before talking about the model, let me quickly summarize the operational environment of the CFDT. At present, the CFDT is being considered for application to inbound arrival flights to Tokyo International Airport, RJTT, which is the most congested airport in Japan. This figure displays the 4 target routes to which to apply the CFDT operation. The routes are referred to as streams 1 to 4. The 4 streams enter the Fukuoka Flight Information Region, Fukuoka FIR, from the west or southwest, and enter the Tokyo Approach Control Area, Tokyo ACA, to arrive at RJTT. The CFDT fixes, which are the target waypoints for time over, are located before entering the Tokyo ACA. To develop the CFDT operational model, we define the related parameters. Each aircraft is assigned CFDT, delta CFDT, calculated by the ATM system. In addition, each aircraft possesses achievable delay, delta D achieved, depending on each flight condition. Then, if delta CFDT is equal to or smaller than delta D achieved, the pilot accepts the assigned CFDT. In this case, 3 of 4 aircraft accept the assigned CFDT, so the acceptance rate, R accept, is equal to 75%. Delta CFDT max is a parameter for each stream, and delta CFDT is assigned within delta CFDT max. To increase the performance of the ATM, a large delta CFDT max is preferable. However, a large delta CFDT max might lead a lot of CFDT rejections and result in a lower acceptance rate. And the CFDT is determined, delta T determined minutes before the original ETA at the CFDT fix. Here, delta CFDT max and delta T determine are the design parameters of the CFDT operation. And this slide shows the CFDT operational model we developed. This figure shows the time history of Mach number. The steps of the CFDT operation are like this. Firstly, the aircraft cruises at M cruise, which is the original cruise Mach number. If the aircraft continues to cruise with M cruise, the aircraft passes at the CFDT fix at the original ETA org. Secondary, the ATM system determines the CFDT delta T determined minutes before the original ETA at the CFDT fix. The air traffic controller instructs the CFDT to the pilot. The pilot judges whether the CFDT is acceptable and controls the aircraft to comply with the assigned CFDT. Then the aircraft starts to decelerate with the deceleration rate AM and cruises at the acceptable minimum Mach number, M accept minimum. Here, the gap between the CFDT determined timing and time to start deceleration, namely processing time by air traffic controller and pilot, is defined as delta T processing. Finally, the aircraft flies over the CFDT fix. Then the achievable delay can be derived at the difference between the actual time of arrival and original ETA. That's about the overview of the CFDT operational model. Next, I will explain the estimation method for achievable delay and acceptance rate. By setting the parameters to the developed CFDT operational model, the model can estimate the achievable delay and whether the aircraft accepts or rejects the assigned CFDT. In this study, we derived the input parameters to the model from the data collected in the CFDT operational trials. So we call our approach as data-driven method. The two trial data are available. One is the trial from 2011 to 2014. In the trial, the CFDT is instructed to the pilot and the speed change is actually conducted. Another one is the shadow operation, which is currently underway. In the shadow operation, several parameters are collected, such as acceptable minimum speed, while the CFDT is not instructed to the pilot in the shadow operation. Here, delta T process and AM are derived from the trial 2011 to 2014, and remaining parameters are derived from the shadow operation data. In addition to the trial data, the wind data is derived from Japan Meteorological Agency and applied to the model. Then the CFDT operational model can estimate the achievable delay. Based on the estimated achievable delay, the CFDT acceptance rate can be estimated. Here, I show you the data examples collected in the trial 2011 to 2014. Each figure shows the horizontal path, altitude profile, and Mach number profile. The horizontal path and altitude are extracted from the radar data, and the other parameters are from the ATM system. For example, the CFDT determined the timing and assigned CFDT. The Mach number is estimated by synthesizing the time derivative of the position of the radar data and wind data. So the Mach profile has oscillation due to the estimation noise, but you can see the aircraft decelerated after the CFDT was determined and successfully flied over the CFDT fix at the assigned CFDT. The error between the assigned CFDT and actual time of arrival was just 0.4 minutes. So the CFDT assignment was success in this case. The purpose to use this data is to extract the processing time, delta T process, and the deceleration rate, AM. But the Mach profile has oscillation. To get clean Mach profile, we applied an optimization-based Mach number estimation method to the trial data. This estimation method fits the model to the trial data by minimizing the gap between the model and the data. The example result is shown in the bottom figure. The orange line shows the estimated result, the clean Mach profile. Then we can derive the processing time delta T process and deceleration rate AM from the estimation results. We applied the optimization-based estimation method to all the available data, including 153 flights, and these figures show the distribution of the processing time and deceleration rate. Actually, several flights could comply with the assigned CFDT without deceleration. As a result, several flights had an excessively large values in the processing time and deceleration rate. To mitigate the effects from these excessively large values, the median values are adopted in the following simulations instead of average values. And this slide shows an example data of another trial, shadow operation 2020. In the shadow operation, the aircraft doesn't actually change the speed, but by applying the data collected in the shadow operation and trial 2011 to 2014, processing time and deceleration rate, then the achievable delay can be calculated from the CFDT operational model. In this case, the estimated achievable delay was 2.2 minutes. So the pilot was likely to accept 2 minutes CFDT assignment, but reject more than 3 minutes CFDT assignment in this case. We conducted the achievable delay estimation for all the available data collected in the shadow operation. This figure shows a cumulative distribution function CDF of the achievable delay. This figure means, for example, in stream 2, the red line, the achievable delay of 65% flights is less than 2 minutes, and the remaining 35% is more than 2 minutes. So if the maximum CFDT assignment in stream 2 is 2 minutes, then the acceptance rate can be estimated as 35%. Then we can derive the estimated acceptance rate of the CFDT in each stream with a different maximum CFDT assignment, like this table. The estimated acceptance rate in stream 1 is the lowest among the 3 streams, and that in stream 3 and 4 is the highest among the 3 streams. In the shadow operation, the CFDT is set based on the several time minutes before arriving at the CFDT fix, but the timing was set as around FUE, Melen, and the tarmac waypoints in each stream. The distance between the CFDT determined timing and CFDT fix in stream 1 is the shortest among the 3 streams, and that in streams 3 and 4 is the longest among the 3 streams. Obviously, the longer flight distance leads the longer achievable delay and high acceptance rate. So these estimation results are reasonable from the viewpoint of the operation. Based on the obtained results, I'd like to discuss the future improvements for the CFDT operations. Back in the introduction, the goal of this study is to design a CFDT operation with a high acceptance rate. And the estimation results show that with long achievable delay, the acceptance rate will be high. So we create the correlation matrix to find out which parameters are important to obtain long achievable delay. This matrix has parameters collected in the shadow operation 2020, aircraft type, stream, cruising altitude, cruising Mach number, wind speed, which is the average along track speed, and acceptable minimum Mach number. The red color means the correlation is strong, and white color means the correlation is weak. For example, the correlation between the acceptable minimum Mach number and cruising speed is relatively stronger than that between the other parameters. However, the correlation between the achievable delay and other parameters are not so strong. So I added one parameter, delta M, which is a difference between the cruising Mach number and acceptable minimum Mach number. The correlation between the achievable delay and delta M is quite strong. Intuitively, the smaller acceptable minimum Mach number leads the longer achievable delay. However, this result implies that even if a flight has small acceptable minimum Mach number, the aircraft originally cruising with small Mach number cannot get long achievable delay. Then the important factor for the achievable delay is delta M, the difference between the original closing Mach number and acceptable minimum Mach number. Based on the results from the correlation matrix, we discussed potential improvements for the CFDT operations. For the near future operations, there are a few parameters that can be changed, such as maximum assigned CFDT and CFDT determined timing. And the maximum CFDT assignment is fixed in each stream. So all the flights in same stream apply the same maximum assigned CFDT, while the achievable delay is different in each flight. We can just adjust few parameters to achieve the intended performance based on the estimated acceptance rate. However, in the future operations, for the future operations, the correlation matrix indicates that if delta M, the difference between the closing Mach number and acceptable minimum Mach number is available, the achievable delay can be accurately estimated on the ground. To obtain these parameters for the ATM system, which is a ground system, an enhanced data link system, such as DAPS and CPDLC, might be required. However, if the ATM system can use the achievable delay, the system can assign the CFDT to each flight within achievable delay of each flight. Then the ATM system can achieve quite high acceptance rate, while the system assigns longer CFDT than the near future operations. Finally, let me summarize the conclusion. To design a CFDT operation with a high acceptance rate, we developed an estimation method for achievable delay and acceptance rate of the CFDT operation by using the CFDT operational model and the trial data. The correlation matrix shows the difference between the closing Mach number and acceptable minimum Mach number has the strongest correlation with the achievable delay among the parameters. Based on this result, we discussed potential improvements for near future and future operations, and we recommended variable maximum assigned CFDT, means that the maximum assigned CFDT is changed for each flight based on achievable delay of each flight. In the future work, we will conduct further analysis with additional data collected in Shadow Operation 2021, which is currently underway. And we will also conduct to estimate the potential benefit from the CFDT operations by using air traffic simulator, which is composed of the ATM simulator and terminal traffic simulator. That's all of our presentation. Thank you for your listening.
Thank you. Thank you, Daichi. Do you hear me, Daichi? Can you see me?
Yes.
Okay.
Yeah.
So we have quite some time to have questions. I have a first question from the next speaker, actually. Is the model considering only the speed control to absorb higher delays? Past stretches along the route might be necessary. Does the model account for that?
Yes, thank you for your question. Yeah, actually, our model doesn't consider the path stretching because it's a TMI just for the capacity demand balancing. In the Japanese ATM, we consider the path stretching is a ATC initiatives. It's not the ATM initiatives. So we only consider the speed control in the CFDT.
Okay. So you don't like calculate any path change or whatever, like extra, like adding some extra routes could be another option, like lengthening the routes.
Yeah, actually, I think in my opinion, the path stretching is one option, but in the Japan Civil Aviation Bureau, they don't consider the path stretching for the CFDT. So okay. If they change their mind, I will try the path stretching.
So we have another question from Olivia Nunez. In Europe, a shadow mode trial for adjusting control times over for ATFM proposes showed limited potential. The calculate takeoff time, the CTOT, works better, and adding the CTO over the CTOT has a lower impact on sector occupancy than was previously thought. Are you using the CTOT also in Japan? Do you have studies on how effective this CFDT operation is for ATFM? Or is it more greater towards arrival streaming, arrival management? Actually, there are three questions. So you can read the question.
Yeah.
So okay.
Yeah, good question. We also conduct the CTOT, the grant delay, the kind of grant delay program, at the present, the grant delay program is working well. However, the reason why we will introduce the Cfdt is to avoid the unfairness between the domestic flight and international flight. Because the CTOT can impose the domestic flight, so the domestic flight get the unfairness against the inbound international flight. On the other hand, the CFDT can impose the inbound international flight. So we will try to introduce the CFDT. And regarding the total performance in the ATFM, we will get the initial result. The CFDT will avoid the unfairness between them.
Okay. So Olivia is answering you as well. An alternative to increase the acceptance rate is to use the ADS-C contract as per ATN B2 standards. The ground, it's the last. Can you see it? It's in the chat. The ground interrogates the aircraft what their maximum and minimum arrival time over the fix is. Means like you first get the constraint, and then the ground can make the decision instead of the aircraft. Have you considered this option?
Yeah, it's a good idea. Now we are considering how to get the acceptable minimum speed. Now we are considering the DAPS, CPDLC, or of course ADS-C. If we get such a parameter exactly, then we can get we will move to the future operations in this slide.
Okay. Then we have two other very interesting questions. For streams passing, like imagine a stream passing through the same fix. That means that you have one flight after another. They're going through the same route. Will flights rejecting a signed delta CFDT gain benefits or shorter flight time? Will they encounter delay later anyway, or there is no incentive for them to game around? Like you can imagine that how honest can they be? I guess it's related to this kind of a problem.
Yeah, it's with the other problem on the trial operations, called some airline will comply with the CFDT, but other airline doesn't comply with the CFDT. Then there are quite unfairness between them. So in the current option, the current CFDT, how to comply with the CFDT is black box for the ground system. We are considering how to provide the incentive to the airline to comply with the CFDT. It's a really good question, but it's future work for us.
Okay. And we have another question from Yu Dong. Great presentation. Will flights rejecting a signed delta CFDT gain, did I ask this question already? Gain benefit or shorter flight time? yeah, it's kind of the same issue in this question, or will they encounter delay anyway? I mean, like, will they have to stack, in fact, when they arrive, or will they? Can they take a chance? That's the question. Can they take a chance to make it faster, or will they anyway have to wait when they arrive? Because this could bias the way they manage their decision.
Yeah. Actually, in this presentation, I just showed the just part of our research called the. Yeah, there are other discussion regarding the buffer to complying the CFDT. If the pilot can comply with just some delay with the assigned CFDT, is it acceptable for the ATM or not? Yeah, there are some various parameters for the CFDT operations. Actually, we are conducting the additional research by using the air traffic flow simulator to evaluate the difference of these various parameters, including the buffer for the CFDT or CFDT design parameters. So this question is one of the our topics in the traffic simulator research.
I have my own question about. So what you noticed very clearly, your presentation was very clear. It was really nice. You noticed that the delta M, what you call delta M, was the key factor, like how much delta M you can offer to the air traffic control to help having the biggest potential delay to the aircraft. Are the airlines open to giving this kind of information to air traffic control? Like, I have some concerns about how much they want to share it or not, because it also gives you a lot of information on how loaded the aircraft is, like if it has lots of passengers or not that many. Plus, it's generally like in the arrival, so the fuel is like, we know that they don't have too much fuel anymore. So we can try to guess how loaded the airline is if they give you this kind of info. Have you thought about this issue, which is very like a commercial issue?
Yeah, it's a very good question. Actually, we conduct the research with the group, including the Japan Civil Aviation Bureau and Japanese airlines. And now we conduct the shadow operation, the cooperating with the Japanese airlines. We have two big airlines, JAL and ANA. They are reporting their minimum acceptable minimum Mach number in the shadow operation. Then we can collect the data, but in the actual operation, they cannot report the acceptable minimum cruise speed in each flight due to the workload. So we have to consider some method to estimate the acceptable minimum speed. One is the data collection, like the shadow operation, and other is to develop the model to estimate the acceptable minimum Mach number. It's a other model than my research. Then, we try to estimate the acceptable minimum Mach speed. We create the correlation matrix to find which parameters is important to estimate the acceptable minimum Mach number. But as you can see that there are not so high, strong correlation in the matrix. The cruising Mach number is relatively high, but we have to need additional research for this issue.
Okay, and I was wondering, like you showed in I don't know which slide you showed, like that from different distances, the fix to the final point, you get a longer possible delay, because the further you are, the more you can delay the aircraft, correct?
Yep.
And so do they have, is it linear, or how does it evolve with the distance? Like, did you do some statistics, like if you try to put different points further away from the destination, how it evolves?
Yeah. Yes, go ahead.
Yeah, I was wondering, like, do you have statistics on how what's the best time to get the best ratio between the uncertainty that you will get anyway, because there is always uncertainty, and the time when the time to make a decision. You understand the meaning of my?
Yep. Yeah, as you said, the longer distance is better for the air traffic flow management, the longer achievable delay. But due to the uncertainty, we have to set the determine the timing. It's also the discussion. It's adjusting in the shadow operation, but we're considering around these waypoints because after entering the Fukuoka FIR, our ground system can estimate the trajectory accurately than the aircraft is outside of the Fukuoka FIR.
Okay.
But so in the shadow operation, that these positions are the best at this point.
The best trade-off. Okay.
Yeah, trade-off.
Okay. Well, thank you. Thank you very much. If anybody else has some questions, you can write it down in the Q&R, and I'll read it to Daichi. I think we had a lot of questions. We're just like ahead of time, like 2 minutes. So if there is no more questions, I will thank you again. Thank you very much for your presentation, which was really, really clear with lots of examples, and it always helps people understanding when you give so many detailed examples on what you did. Thank you very much.
Yes, thank you very much for the fruitful discussion. Thank you.
So, hi everybody again. We're moving in time from 9 p.m. to what is it now? 9 a.m. something like that. In North America, it's my pleasure to introduce Gabriele Enea, who is a technical staff in the ATC system group at MIT Lincoln Lab. He has a PhD in transportation engineering from the Università degli Studi di Palermo in Italy, which is next to France. So I'll let you introduce your presentation. Again, people who want to ask questions, you can either use the Q&R or the discussion box and write it down. I'll be happy to read it to the presenter at the end of his presentation. I give you the mic, Gabriele.
Thank you, Nicola. Good morning. Right now it's 9:50 here in Boston at a time check. So today I'm going to talk to you about some work that we did in trajectory-based operation, and I'm really happy that of our previous presentation, because I see that they're also starting to do, or they've been doing time-based metering in Japan. The thing that I noticed is that we do similar thing, but we call things in different way. So the Cfdt that was presented before, we actually call a scheduled time of arrival. But the concepts are similar, and it's good that we are working on similar problems around the world. First of all, I want to start with acknowledging my colleagues, Michael McFarland and Timothy Boning. Today, I'm going to talk to you about some work that we did looking at the aircraft speeds that are used by the TBO system here in the US, and then on the impact of providing different wind quality information data to TBO systems. All right, but you got a little bit of an introduction on what is TBO, I guess, in Japan in the previous presentation. What we consider what is basically TBO is trying to do move from separation that is based on distance into separation, imposing separation using times. And in the US, these are going to be supported by 3 fundamental automation. On the ground, there's going to be the terminal flight data manager. Then the traffic flow management system provides capacity demand imbalances in different resources in the NAS. And then the cornerstone of TBO in the US, it's the time-based flow management. The time-based flow management does provide schedules of to the air traffic controller at different meter point along the route. And if you can see here, in the US, we also have some things called extended metering. So in theory, some aircraft could have multiple meter times along their route. Of course, when the weather conditions are favorable, are nice, the winds are easy to predict. You know, the systems have a good accuracy in predicting the speeds of the aircraft, which are very important, as you can imagine, to achieve those meter fixed times. And moreover, when there is no convective activities, the routes of the aircraft are very stable. They don't make a lot of changes. The systems have all the information that they need to create these plans and to present a schedule to the controller. And if you see here, this is an example of the meter fix. On the right, you have the scheduled time on arrival, and on the left, you have the estimated time on arrival. And controller have some little notice of how much delay they have to burn to actually have those aircraft to match their schedule. But I guess weather is not always cooperative. Yeah, and so perhaps you can have issues with days in the NAS where the winds are very strong, and perhaps the systems have a hard time capturing winds that are very strong and fastly changing. And this affects their prediction of the speeds of the aircraft. So, for example, when you're climbing out of an airport, your speed might be inaccurate. And so the time that you will arrive at this meter fix might be maybe inaccurate because your speed is inaccurate. Then when you get to cruise phase, the convective weather could impact the routes of the aircraft. And you know, when there is convective weather, aircraft start flying very tactically. And therefore, their routes are not accurate anymore into the automation, because some of these tactical changes are not always inserted into the system. The controllers have a lot of things going on that case. And this actually results in inefficient or infeasible time targets. So the schedules that I showed before become less accurate because the information provided to them, or they're not accurate anymore. And so when you get close to the airport, you might encounter holding, and then when you have in the terminal, which is when you're lower, you might have path stretches and things like that the controller have to do to maintain the separation to keep the sequence of aircraft. And if you don't believe me that you know, convective weather and winds have a big impact on trajectory-based operations, yesterday there was a meeting that was after the end of the last session at the ATM seminar, in which NASA and FAA were sharing some information. And this is one of the slides that was presented by one of my colleagues at the FAA. And of course, the issue is that at the when this condition actually causes, a lot of times the automation is turned off and they revert to less efficient types of control, like miles intra-airs operation, other routes, they're very conservative. And so the automation that you need in these cases to deal with this challenging condition is basically not helping you. But how is the system calculating, at least in the US, those schedules? They start with having supporting data that are native aircraft performance model, airspace adaptation data, and then they also have to take flight plans, track data, ground speed from the automation that is called ERAM in the US. And then they use the only weather information that TBFM is using right now is the rapid refresh forecast. This is an hourly forecast with the 40-kilometer grid. As you can see here, there is no trace of any convective weather information, and therefore TBFM has no way of knowing where those weather cells are in the routes, and now those changes. So current wind data and lack of convective weather in TBFM is really insufficient in a challenging meteorological condition. So what we're doing here at Lincoln Laboratory is to create a testbed to analyze TBO issues in these cases. In the remainder of my presentation, I'm going to give you a brief overview of what we're building here at the lab, and then I'm going to talk to you about some data analysis that we did to identify some of the quality of the adaptation data. I was talking about the speeds and also the wind information, and then I'll close up with some future vision and a summary. So what are the key data research questions that this problem actually needs to solve? First of all, what are the supporting data that can improve TBO automation? What are the wind data requirements, for example, the grid size, the update rate, they are necessary to support TBO outputs during challenging wind conditions. And then what are the benefits? The increased throughput, increased accuracy, and the cost. These are systems that are actually working in the field right now. So there is no infinite power, computational power. There is problem with bandwidth. These problems needs to be studied. And what we're creating here at Lincoln is basically a sandbox to study all these problems. And the key characteristics are that we have the version of the operational automation system. This is the system that is used by controller in the US. We have the ability also to integrate R&D enhancement. There are some R&D versions of these systems that were developed by NASA that are actually do start to include the convective weather into it. And then also we want to have the ability to explore what are the impact of wind and adaptation data inputs change the trajectory prediction algorithm in a safe environment before these changes are transferred to the FAA. And we're developing this as a which is a key component of our testbed together with the FAA Technical Center in Atlantic City. How does this look? As I was saying before, we have the TBO system at the center. So we have TBFM, we have DRAW, which is the dynamic routes for arrivals in weather. This is basically a prototype version of TBFM that was developed by NASA, and it does use some convective weather information. We also have access to TSAS remotely from the tech center, and TSAS is the extension of TBFM in the terminal area, and it supports controller to continue the time-based metering in the terminal area all the way to the runway. And then what we wanted to do, we want to excite and study this system with different weather forecasts. Of course, we have the operational rapid refresh that I was talking before. We also want to test the improvement that you can reach using the HER, which is the high resolution rapid refresh. This is basically this an improved model that has a finer grid and a more frequent update rate. We also want to test the impact of a different convective weather avoidance model. We here at Lincoln have a history of studying convective weather impacts into air traffic and air transportation. And so we have many different models of convective weather, and we can feed those to the systems. And then in the future, we want to study the impact of real-time winds that can be are now extracted from different sources. We have MODES EHS radars that we can interrogate. And I'm glad to see that also yesterday there was a presentation from our friends in Spain that actually are looking to use these data to improve the wind the wind predictions. And of course, you have to drive this system with different type of trajectories. You can play back TFMS flight plans. We can use this trajectory generation facility from the FAA that we can access remotely. And then, of course, we can go to very high level of fidelity and use, we have a version of the Pegasus FMS that could, in theory, drive this system. And the output are to inform the impact of different wind and weather models on TBO system, identify what are the changes that are necessary to take advantage of these improved models, and then to quantify the cost and monetize the benefit of integrating each model. And if you want to have a snapshot of our lab, you see we have draw here, which is the dynamic routes for arrival during weather. We have TBFM schedule in the draw version. We have CWIS, which is the corridor integrated weather system. This is one of the weather products that are currently used by TMCs in the US. And also the TFMS traffic situation display, which gives you really a panoramic on where is all the traffic, where are the weather issues, and therefore so you can do like those high-level planning. And what we have studied and what I want to talk to you in my presentation today is, first, we started to look at the descent speed data. TBFM uses tables of descent speed for each aircraft airframe, and we wanted to look at how this compare versus how aircraft are actually flying right now. And we did this using some modest CHS data. Then we also wanted to look at how these TBO systems are impacted with, or how their performance could improve with using improved wind information without changing anything else in the software. And then in the future, as I was saying before, we wanted to study what are the data that you can actually extract from the aircraft to improve your prediction on the ground. You can ask for the sense winds, and the winds, then you can use them to improve the forecast, or you can use their sense speeds. Those are very accurate, very frequent update things that right now are not used by any ground automation. And so now I'm going to talk to you a little bit about those couple of analyses that we did. First of all, I guess for this audience, it's not very important, but what is modest CHS? So we have access to actually a couple of radars. We have experimental radars here at MIT Lincoln Laboratory, and then we also can use an FAA radar, which is down in New Jersey. Modest CHS is basically an aircraft. Most radars in the US can be modified to actually interrogate the aircraft to a different registry and ask for basically readout of their ground speed or their Mach, CAS, and other information also in the intent field. And what we did, we used some recorded data from the radar in New Jersey of aircraft that were arriving into Philly. And what we wanted to see using this data was basically two questions. So as I was saying before, TBFM uses adaptations. There are basically tables for each aircraft type. You have one descent speed. And we wanted to test two questions. One was, what is the difference between the speeds that are used by TBFM and the one that we are sensing from the modest EHS? And to answer the first question, you can see this is a box plot, and you can see the blue dots are TBFM table version, descent speeds for Philly, and the box plots are what we were observing. In general, we see that TBFM overestimates. The difference are not huge, but this was actually a known fact. In fact, from the literature, you can find that when TBFM, the predecessor of TBFM, which was called TMA, was designed by NASA, was actually designed to predict to use speeds that are slightly higher than the one that are used in the field. And this was done to what they call front load the schedule. So they wanted to kind of like try to maximize, keep the pressure on the schedule and to maximize the throughput. So this was kind of expected. The next thing that we wanted to test was whether aircraft fly different descent speeds depending on the starts into Philly. So we had the most amount of data for 3 different stars, and you can see the data here. And the good news is that most aircraft, especially the more recent one and the one that have the most amount of operation, usually a very small difference between the speeds that they use for different stars, which means that in theory you probably don't need to adapt different speed for different stars. Of course, there are some aircraft types that that have a little bit more of variation. And in this case, we observed that the one that had the most variation were the older airframes. And these are data from before the pandemic. I would not be surprised if most of these aircraft by now, after we return to a normal level of traffic, are basically already off the line. And so this probably might not be very problematic. And the difference is still in the 7-8% real. So again, to answer the question about the variability, probably you wouldn't gain a lot in terms of performance by doing an adaptation for each star for each aircraft type. So the next analysis that I want to talk to you is was done on some wind data. The research question that we wanted to test was if we don't change anything in TBFM. Remember, this is an operational system. What can we gain without changing anything in software? This is very expensive to do for a deployed system. If we just change the wind information and provide better wind information to TBFM without changing anything in the software. And to test this hypothesis, we work with our colleagues and friends at the Tech Center. So we use, again, TBFM playback data, but these are different data set from the previous analysis. And we selected 5 days. We wanted to look at days where the winds in Philly were actually high, and we identified 2 days right before the pandemic hit. So the traffic levels were still pretty good. And then we identify also 3 days with low wind to compare and see if the impacts were different. And for each one of these days, we collected 5 hours a day, 5 hours, which gave us about 200 flights. So we had a good amount of flights. And to test, what we did is basically simplified in this chart. You basically see we run playback data. We fed that to TBFM 4.8.4, which was the fielded version at the time. And then we run it twice, once with the operational winds, which are from the rapid refresh, and the other one with her derived data. And I will explain to you a little bit more in the next slide why I call it her derived data. And then what we wanted to test was the output, was the ETA accuracy. How is TBFM predicting the time of that the aircraft is going to cross that meter fix compared to what actually happened? And so to do that, we used this test called the cone test. This was a performance test that was used by the FAA to actually evaluate new version of TBFM. And the cone represents basically a bounding on the error. Here you see the time to the meter fix, 20 minutes to 0. And here you see the meter fix ETA error, which is basically your actual time of arrival minus the ETA at that time along the route. And therefore, this error must be, to pass this test, must be bounded of plus or minus 60 seconds, linearly decreasing to 10 minutes, and then plus or minus 30 seconds after that. Which means that as you know, the prediction, the time prediction of system usually improves while you get closer because you have better information. And in this case, this aircraft is actually inside the bound. And the plus or minus 30 seconds comes from an accuracy requirement. As I was saying before, TSAS is a terminal version of TBFM. And there is a study that was published in the literature that say that to actually have functioning terminal metering, you have to deliver at the meter fix aircraft with an error of plus or minus 30 seconds. As I was saying before, we basically use fed TBFM herd derived information. And what do I mean derived? So HER is a 13-kilometer grid and can be a different update rates, but we use a 1 hour update rate. We started with the 0 hour forecast. This is called the analysis data, or for wind accuracy studies, the truth. So this is the closest thing. After the hour is passed, actually, those are the winds that were sensed by the sensor that you have in a specific site of the area. And therefore, this is the most accurate thing that you have. Of course, you cannot use that in real time because these are compiled after the hour is finished. And then what we did, we interpolated this data into a 40-kilometer grid. As I was saying before, TBFM, we didn't want to change anything in the software, and therefore we have to feed data in the same format that TBFM is using right now. And then we moved the time step. We basically tricked TBFM to say this hour was the truth hour, but we changed the timestamp to be an hour forecast. So TBFM thought that truth hour was actually a forecast, and we ran the data that way. And now, what are the results? When you do this process, the granularity and the great amount of information that you have on a lower grid, on a higher resolution grid, they are somehow lost. You start with better information, but still the granularity has to go back to the same that the system can process. So to look at some results, this is basically the I picked one day just to show an illustration of the data, and for all the aircraft in that specific day, with the baseline, the root mean square error was 126 seconds, and with the improve was 124. If you want to look at how many aircraft actually met the stringent requirement, so how many, for example, were in those plus or minus 60 seconds in the meter at 20 minutes from the meter fix. With the baseline, we had 110 flights, and with the improved data, we have 112 flights. So a small improvement. And finally, if we want to go even to a further improved accuracy, and we want to see how many aircraft actually met a 30-second requirement at 20 minutes from the meter fix. With the baseline, we had 61 flights, and with the improved, we had 70 flights. So there is a small gain, but as I was saying before, without changing, we are making changing in the software to actually use more finer grids of the wind. You won't get a lot of gains. And the last thing that we wanted to see was our high wind days impacted differently in terms of the performance of TBFM. And we noticed like some small differences. For example, in the high wind days, there were actually the improvement is pretty constant. If you pick the top 10 flights, so these are the best flights performing with the baseline, your error was 15.7 seconds. With the improved winds was 11.9 seconds. This is an improvement of 24%, but what does that mean? Like if you have a schedule that is accurate to 15 seconds, if you won't see the difference operationally if you improve that to 12 seconds. So again, small gains, perhaps in high winds more than in low winds, because in the low winds we actually saw that for some reason the baseline winds is basically the same or actually better than with the improved winds. So without changing, again, software and the way that the software works, which is very costly for the FAA, you won't get a lot of gains even changing the wind information. All right, let me wrap up now my presentation with a fusion vision and a summary. What would be a weather-aware TBO system? Well, how would they work? So think about like systems that have information they don't have right now. Before taking off, you could think about TFDM already identifying, the meter fix, the departure meters that are not blocked by the weather. And so you would start by already taking off and keeping your schedule there. Then you can think about getting TFMS, some information to identify clear path, and basically having those information reflected into the capacity demand balance. And then when you get close to the to arriving to the airport, you can think about system like draw that can identify clear arrival routes and the fixed that are not impacted. So you could keep a schedule, you can keep doing the time-based metering even in convective weather conditions. And of course, you can think also about improving the wind information, that if you have a day with very strong winds, they are changing very quickly, you can still have good speed prediction of the aircraft that can help you to keep maintain an accurate schedule. So again, this is a vision. Most of these systems don't have this information right now, but this would be a way to continue doing the time-based metering, doing convective weather and wind and strong wind conditions. What are the other things that we think we need to be studied? Of course, the integration of the three systems. These three systems use different trajectory generation. They have different requirements in terms of wind, weather. What is the 3T integration, as we call it here in the US? Like a gate-to-gate weather where TVO optimization, but what are the data that these three systems needs to share? What is the air-ground trajectory interoperability? What are the requirements? And really, what are the benefits? As I was saying before, and I've seen different presentations in the seminar, which I was very pleased with. There is more availability of data that come from the aircraft, but of course, the aircraft doesn't have kind of a vision of what's going on around. So, what are the data that we can extract using MODAS, CHS, using EFPs? And send them to the TVO system to improve their schedule. There are some things that the ground can do better, and there are some other things that we can get we can get from the aircraft. And then finally, the FAA is already thinking about 2035. What's going to go after this system? They are very monolithic. They're very big, large, complex software automation, and they have a lot of adaptation that needs to be maintained. How do you design a system different? What if you, while you're still, of course, maintaining and improving this system, start thinking about designing an all new architecture for the entire system? And so we are thinking about an enterprise trajectory service, which would be a completely different architecture, more service-oriented, more thinking about the application like advanced air mobility. And we're glad also that we're starting to work with NASA on thinking about those things of the architecture and the requirements for basically rebuilding, redesigning a system for the future. All right, I hope I have convinced you that the accuracy of descent speeds and wind data reduce the operational effectiveness of TBO automation system. We are here at Lincoln are working very closely with the FAA to build this sandbox. We're excited because it's kind of like playing with the, we have a lot of toys, and now we are feeding them different things and seeing the outcome. So it's really a lot of fun to do. And then the best outcome for something like this would be to develop a roadmap of studies. What are the things that what are the research questions that still need to be answered, and what are the studies that can support obtaining those questions, those answers? This is really what we would like to have at the end of in the next 10 years or so. And I hope also you like our logo. And this is the end of my presentation. So I'm very happy to answer any questions.
Thank you, Gabriele, for your very detailed presentation and giving examples of what you analyzed. I'm saying it again, I don't have any questions in the Q&R question right now, or in the discussion right now. So while people are maybe writing it down right now, I'm going to ask a first question. So you were talking about the small gain. Can you come back to that? Yeah, this one where you have 61 flights on the left and 70 flights on the right. I was wondering, maybe my question is naive, but is it possible that there is a real-time adaptation of the airplane's attitude to compensate the errors that is done on simulation, or is it done on it's real trajectory?
Yeah, so these are actually real aircraft that flew, and then we basically tested what this automation would have predicted for those exact aircraft with two different wind information.
So okay, so is it possible that on the left side it's really what happened, so that there was some kind of better results than, because they try to compensate the real wind and the real error, and on the right side you don't have this? Maybe I'm not clear in my question.
No, I think I understand what you're saying. So the answer is no, because the actual time of arrival, so the actual time that the aircraft actually crossed the fix is fixed because we have the real data. So we know when the aircraft there. What we are changing is basically what is the prediction that every minute or every 12 seconds, the automation is doing based on the information that you had at the time. So we're basically seeing what is the how the prediction changes, but the actual time is fixed.
Okay. Were you hoping to have better results, or were you surprised by those results?
No. Well, so we obviously we were hoping to have some better results, in the sense that we started. So what I was saying before, we started. These are called the truth wind information. So basically, these are wind and weather products. So they're all models. There is nothing. There is no truth in wind.
Yeah, I get it.
But after the hour passed, so NOAA produces this forecast every hour. And then when the hour passed, they basically collect all the information that they have from the sensor and say, this is what we forecasted. This last one product for this hour, this file is what we call the truth, because it's what we saw during the hour. So you can't actually feed that truth to the system because it hasn't been built yet, you know?
Yeah.
So we trick that. So we were hoping to see, well, so this tells you one thing, that basically the forecasts are already pretty good. But then there was another thing that we have to, consider. As I was saying before, TVFM can only use grids of 40 kilometers. The one that we used started from 13 kilometers. So in theory, if you had the information, you could have more information in the middle of your prediction. But then you lose that because the software cannot actually ingest those data. So we were hoping a little better, but we weren't super surprised that the difference wasn't bigger than that. So it was kind of like a proof of, we want to answer one question. If you don't change anything in the software, can you actually gain something? The TBFM is a massive system, is in every center in the US. Every software change, the contractor charge, for good reasons. This is a production system. This is a system that is also used by controller. He charged a lot of money to the FAA. So the first question is like, well, if I don't change anything, but I can improve the supporting data. So if I can change one file, which I'm just taking it from a better source, would I get any gain? We kind of answered to the question and say, like, really there's not a huge amount of improvement if you don't change the software.
Okay, well, it's very interesting. There's also might be a gap between the truth, what we call the truth, and the truth, which is like the real wind. I mean, like they built it's still like an evaluation of the wind that happened, but maybe it's not exactly what happened. So it's challenging, and I really appreciated the title of your your paper, evaluation and not prediction, because like that's kind of being modest about what we can achieve or not achieve. And so it was very, very nice of you to call it this way. Is there any other question in the audience? Or people are already having their coffee break? We still have a minute or two. You said you talked at the beginning of your presentation and at the end of your sandbox. Is it like, so this is a very general question, is somehow one day people gonna share the sandbox with other researchers around the world? Or, I mean, it would be, you have a great amount of data, and maybe it would be interesting for people to use those data. Is it?
Yeah, well, so there are many. So we are a university. You know, we work from the government, and we're kind of in between, because we are MIT, but we're also funded by the government. So we are definitely open for collaboration. I think the thing that to really excite me and us is putting together different pieces. So the cool thing about our sandbox, and you know, you can think about how to collaborate in this way, is that we have the operational systems. Of course, these are not online. We have our own instantiation, so we can try whatever we want. But then, well, whatever we try is going to be saying, okay, you try in the real system. So we're not making a model of these are the systems the controller use. And the thing that I think it's the more ripe information, and it's good. It's interesting that you said that. I want to reach out to a couple of the people that presented at the seminar, because we want to explore different way of using the data that come from the aircraft. This is far term. You know, this is complicated in the sense that the system have their own, weather feeds. They have their own information feeds. But what if you can study and create requirements for what are the best information you can take from the aircraft? And there are two things that I think are really interesting. So you can use the data that the aircraft sends you to tell you things like the speed that I'm flying, the speed that I want to fly. But you can do another thing. And then you go back to the wind discussion that we had before. You can actually take the wind that the aircraft is sensing and then use that not to improve directly the system, but to improve the weather forecast. So you can think about creating a way.
It's a circle, yeah.
Right. And so those are the things that if there are people that have done some of this work and they we would love to think about the models, and then we feed them, and then we share the results, and then we write papers, and we'll see you in 2 years at the next ATM Center.
Yeah. So thank you again. It was really nice. We'll have our coffee breaks, everyone in his own area. Unfortunately, it would be really nice to talk to you around a coffee. I'll meet you again in 10 minutes for the last two presentations. So be on time at here in France, it's 4:40, and then you make the math to know. Well, it's in 10 minutes, whatever. Okay.
Thank you so much, guys. Thank you for the attention.